Now we get to problem 5, which is also optics problem. It says find the apparent depth of a coin which is inside ethanol, n equals 1.36, at the depth of 15 centimeters. And you are looking at it from air. So we want to know the apparent height of an object that is inside of some medium. And we want to be able to use the equations to solve for that. Also find the critical angle for the coin to not be seen from air. Okay? So let's say we have some kind of medium here. And there's a coin here inside of the medium. The n is given as 1.36. Well, we talked about this before. When the light rays come from here, from the heavier medium to a lighter medium, they bend outward. They bend outward. So what's going to end up happening is these light rays going to go back. They're going to appear to be coming from higher up, right? So something that is in water or some kind of medium is going to appear as if it is closer to the surface, right? How much closer, right? Well, it's going to end up that the apparent depth, d prime we can say, is equal to the actual depth divided by the index of refraction of the medium, right? If this one also had a certain index of refraction, n of, let's say n1, n2, it would be the ratio of them. So if this one is larger than that, it would be the larger one on the bottom, the smaller one on the top, right? So if it was, for example, 1.36, and if n1 was 1.1, it'd be 1.1 over 1.36, right? So it would appear again as if it was closer to the surface, right? So as long as this medium is lighter, the object looks as if it is closer to the surface. So in this case, the index of refraction of air is 1.0. So this one is just equal to 1. And then the actual depth is equal to 15 centimeters. And then this one is equal to 1.36. So if we divide those, the apparent depth, it's actually not this drastic. So the coin appears as if it is only 4 centimeters up. So a more realistic picture would look like it would be here 15. You would go here, bend, go here, bend. The coin would appear here. So it goes 4 centimeters up. Its original height was, its original depth was 15 centimeters, and it looks as if it is 11 centimeters from the surface, right? How about the critical angle? The critical angle, well, we've talked about that before. At a certain angle, the light rays bend in such a way that they do not go out, right? This critical angle is 90 degrees. 90 degrees. So how do we find that critical angle here? Theta critical. Theta critical. It's not necessarily the edge of the surface. So the surface could be this wide, right? So it would be this angle that it's making from the normal line, right? So, well, I've solved those before. So remember how we do it. We say n of the n2 sine of theta critical is equal to n1 sine of 90. And this becomes 1. So in this case, sine of theta critical is equal to n1 over n2. So in this case, 1 over 1.36. 1 divided by 1.36, so that's equal to 0.735. And then you take the inverse sine of that. You get 47.3 degrees. So theta critical is the inverse sine of 0.735. And then it comes out to be 47.3 degrees. Okay? Now, let's actually analyze this a little bit more detailed, this apparent depth concept. So let's draw it this way. let's draw it kind of horizontal so you can see it a little better. So you have a certain medium here, index of refraction 1.36. You have another medium, index of refraction 1. You have an object here. We want to know where is the image of that object as displayed in this from here, right? So what are the equations of that? Well, the equation that we're going to use is N1 over dO. So N1 is the index of refraction of the medium in which the object resides. So we're going to call this N1. The coin is in that object, right? The N1 coincides with where the object is. Plus N2. N2 is where we're interested in. Where's the image of that object as viewed from an observer in the second medium. So we'll call this N2, N1. N2 over di, that's equal to 1 over the focal length. 1 over the focal length of this lens right here, right? So think of this as the interface of the two mediums, and think of this as a lens. Right? Now, to find the focal length, this is the equation I use. I say 1 over f is equal to the index of refraction of the medium in which the lens is, N1, minus the index of refraction of the surrounding. So if the surrounding was some other medium other than air, we would use its index of refraction. So I'll just put here N2, okay? And then divide that by what? The radius of curvature of this side of the lens, right? This side here, the radius of curvature. If we were looking at the image from this side, we would be using the radius of curvature of the right side, right? But if we look at it from the left side, we look at the radius of curvature of the left surface, right? So that gives you the equation for the focal length. Well, since this one is not curved at all, it's flat, what is its radius of curvature? Okay? Well, you could visualize it almost as if it is an infinitely large sphere, infinitely large, it just keeps going and going and going. Where would its center be? Way over at infinity, right? So objects that are more or less flat, their radius of curvature is infinite, right? So this one here is infinity for flat objects, right? Therefore, what is the focal length equal to? Well, 1 over f is some number over infinity 0. The focal length approaches infinite, okay? So therefore, focal length infinity means that it is actually acts like a weak lens, right? The smaller the focal length, the stronger the lens that it acts like, right? So this is a very, very, very weak lens. So if you put infinity here, 1 over f is 0, so 1 over infinity is 0. This goes to 0. So how do we find the image distance? Well, we have here N1 is equal to 1.36 over 15 plus N2, in this case is air, over di. That gives you 0. So we have 1.36 over 15 is equal to negative 1 over di. Di is equal to negative 15 over 1.36, and that gives you your negative 11 something something. So it gives you the same answer as what we got a minute ago by saying the apparent depth decreases by a certain amount. But this way of looking at it is more general, more detailed, and it can be used for any other kind of problem, right? Notice if the image distance is negative, this means that it's actually a virtual image, right? So the object is here, the light rays are coming from here, bending outward, and it's producing an image here. So it looks like the rays are coming from here. They never form an actual image in this medium, okay? So the image is not real, it's virtual. It appears as if it's coming from inside of the medium, and that's what it means to say the image distance is negative. The image is virtual, right? So this way of doing it is a more detail-oriented, okay? So now let's actually apply this to a certain surface. Let's say instead of ethanol, this represents a certain glass medium, okay? And then what I'm going to do is give it some curvature, okay? And there's an object inside of the glass, and we want to know where is its image going to be. I'm going to look at it from this side. the curvature of the other side is not going to matter, right? So what is it? Let's give it some radius of curvature. Let's say the radius of curvature is equal to, it could be some random number, 50 centimeters, right? So that means it's part of a sphere, the radius of which, remember our object was 15 centimeters, so that means the radius of curvature is a lot bigger, right? So our object is somewhere here, right? So this represents part of a sphere like this whose center is 50 centimeters away, okay?